The geometry of the capacitor is important to find out the capacitance of the capacitor. To simplify the calculations of capacitor for different geometries, it is sensible to develop a general strategy. Four steps are mainly involved to find out capacitance of a specific shape. So the first is presence of charge Q on the plates. Second is calculation of electric field. Between the plates in terms of this charge using Gauss's law. Third is calculating the potential difference from the derived electric field. And final is the calculation of capacitance. Q is equal to CV. So to relate the electric field E between the plates of a capacitor to the charge Q on either plate, can use Gauss's law. So, and we know Gauss's law is E dot dA is equal to Q. Here Q is the charge enclosed by a Gaussian surface, and this integral E dot dA is the net electric flux through that surface. In all cases, the Gaussian surface will be such that whenever there is electric flux through it, E will have a uniform magnitude E, and the vectors E and dA are parallel. So this equation reduces to in which A is the area of that part of the Gaussian surface through which there is a flux. We already studied this in previous chapters. So for the convenience for the calculation of capacitance, we draw the Gaussian surface in such a way that it completely encloses the charge on the positive place. For example, this one. Now, the potential difference between the plates is related by the electric field. So we will use the equation which we studied in the previous chapter. In which the integral is to be evaluated along any path that starts on one plate and ends on the other. We shall always choose a path that follows an electric field line from negative plate to the positive. For this path, E and DS will have opposite directions, and the dot product becomes minus E dot DS, and the right side of the equation becomes positive. So, so your potential will become V is equal to negative to positive E dot ds. So this equation and this equation becomes the generalized form which we can use for any configuration of the capacitor. Now let's consider the most popular case, which is a case of a parallel plate capacitor. Let's assume the plates of the capacitor are so large and so close together that we can neglect the fringing of the electric field, this one. this fringing. So we draw a Gaussian surface that just encloses the positive charge on the positive plate, and Q is equal to epsilon EA. Potential difference is equal to this, and in this case, because potential is equal to minus to plus E ds, it becomes, in this case, E is constant, it will be out 0 to d ds, and potential becomes ed. Now we can find out capacitance by using q is equal to cv and the value of the potential. Q is equal to cv and capacitance is equal to q over v, which is equal to q divided by E into d. And here we know from this equation that q is equal to epsilon naught ea, so just use that value as well. So it becomes epsilon e a over e d, and the capacitance is epsilon a over d. This is the capacitance of a parallel plate capacitor, and it shows that capacitance is only dependent on geometrical factors, the plate area and the plate separation d. So capacitance increases if we increase the area, and capacitance decreases uh, with separation d. Uh, yes, if we yes, they are inversely proportional. So if we decrease the spacing between the plates, capacitance increases. So now let's do the same calculations for other configurations in the next video. Let's move to the next video to have a look into the configurations.